Okay, so I suppose I will start. Excuse me for the delay. Uh, so I welcome you to this problem solving and live interaction session for the subject experimental stress analysis. So today we will be just going through a recap of all the sessions that we have previously discussed. So I'll just start with the first one. So the question says, from the contours given below, identify the fringe patterns which matches with the U displacement obtained in the case of a cantilever beam with an end load. So what is given? So we know that when we have gratings, when we are trying to measure U displacement, we have the technique of Moire, where basically we have two sets of gratings. One is the specimen grating and one is the marker grating. So we attach one to the specimen and then view it with the other grating to see the movement that is brought about from the mechanics of the problem onto the model would reflect as fringe patterns as we see here. So one rule that we have seen about Moire is that the displacement is measured perpendicular to the grating direction. In the case we have a grid as for a grating, the patterns that we see would essentially be representing U plus V. Whereas here in this case we are able to see the grating directions here. These are given to be horizontal, which means these are showing displacements that are along this direction. So generally, if this is x, this is y, the displacement that we associate with x is u, displacement that we associate with y is v. So the question is asking us u displacement, which means if the displacement to be measured is this way, then the grating must be kept perpendicular to that. So from this, we can see that these two are choices that are viable. B and D don't match this criteria. So what we are looking at A and C are indeed U displacements. Now the question comes, we have to be problem specific now. The question says this is for the cantilever beam. Now we know that a cantilever beam with an end load is not a symmetric problem. And from this very problem, we can see that U displacement is symmetric about these two axes here, which is why this cannot be the answer. Hence, this C represents the U displacement for the cantilever beam. So, are there any questions? If there are any questions, you please feel free to ask. In the meantime, I'll move on. Yeah. So, should there be any questions, please feel free to stop me and ask. And then once we did with Moire and other techniques of experiments, then we moved on to bring our focus into photoelasticity, where we generally have two types of elements. One is a polarizer, which restricts, absorbs light in one direction, or rather, I should say, it it transmits light along the polarizer axis. polarizer axis and absorbs everything else. And then we have retarder plates that can be a quarter wave plate, a half wave plate, full wave plate, and so on. So with that in mind, if we look at this question, the given figure represents the output light intensity of a light wave after passing through the polarizer and analyzer. So what we are looking at here is a polariscope setup where let this represent the light path and let this be the light source. Let this be the light source. I have the first element, that is the polarizer, placed like that. And then I have another polarizer, but I'll place it at some arbitrary angle. I'll place this polarizer with some arbitrary angle and I will be viewing the light from here. So this is the viewing end. This is the viewing end and this is at some angle. Since we are trying to study the light that is coming out of this, essentially we're trying to analyze that light, which is why we call this an analyzer. Just to differentiate this from the polarizer, essentially both are polarizing sheets only, linear polarizing sheets. Okay, so the question says that initially the polarizer and analyzer were kept parallel. So what this is saying is initially this analyzer was kept like that, parallel, and then the analyzer was slowly rotated by 90 degrees, keeping the polarizer stationary. So this is kept stationary. What we are doing with this, it is initially kept at 90, then we are slowly changing the angle like that. Now it says arrange the following figures according to the increase in the angle between the polarizer and the analyzer. So if this is theta, initially when this was kept parallel, the difference between the polarizer angle and the analyzer angle is zero. So initially it was zero. Initially both were parallel, so initially it was zero. The angle was zero. And then it slowly increased. And if we were to place it like this is the maximum, that is 90 degree. And then going forward, again it reduces. And if I were to place the polarizer in the opposite direction also, it is one in the same. This and placing it this way is one in the same. One and the same. So that is also at 0 degrees. So it is asking from 0 as we move on, how the light would have looked. So we can see here, if we were to see this in terms of intensity, let this be ID, let this be IC, IB, and IA. So from the figure, we can see that ID has a greater light intensity, then comes IB, then comes IA, then comes IC, where C we are able to see that it is almost pitch black. So this implies that polarizer and analyzer are kept perpendicular to each other so that whatever light comes out of the polarizer is directly getting cut, totally getting cut out of the analyzer. So in the terms of increasing angles, according to the angle, increase in the angle between the polarizer. So we have to go from 0 to the maximum angle. So when the maximum angle is there, we will have no light. When it will be 0, it will be full bright. So we can see from full bright. So this is angle is 0, then 0 plus some, call it some theta, not theta, let me call it some beta. So 0 plus beta plus some alpha, and then totally this is cut. So this must be 90 degrees. So we have already arranged it in the increasing order. So the answer would be D, B, A, C. I take it is clear. Okay. All right. So let us look at this question. It says if the location of the point where the measurement of stresses has to be carried out is known a priori, the preferred experimental technique for precise measurement is which of the following? Now we know that brittle coating, photoelasticity, and holography, basically brittle coating, photoelasticity, these are all whole field techniques, which implies that if we have the domain of the problem like that, whatever be the domain of the problem, we will be, when we conduct these experiments, we will be able to get the information throughout at every point in the domain. Whereas if we see a strain gauge is a point by point technique. If I were to paste a strain gauge here or a rosette here, I'll be able to measure the strain at this point along two or three directions, which howsoever I place it. But essentially, I'll be able to analyze this test the state of strain only at this point. If I were to find it out here, then I'll have to again paste a new strain gauge over there. So essentially, strain gauge is a point by point technique. However, strain gauge has a better resolution in the sense that if the experiment is conducted properly, following all the recommendations, the strain gauges that come nowadays can even measure up to 1 or half microstrain, which is an extremely small quantity. However, if when we are actually conducting an experiment, our interest is to find out where the specimen or the stresses peak, where the specimen would fail or where the stresses are peaking. So that is our motive because we want to design the product or the component for that against failure. In that case, the whole field techniques, given that these give us the entire stress or strain field throughout the domain of interest, if we can identify where the stress is actually peaking, then we can go ahead, go zoom into that point essentially and make finer measurements. So in this case, the question says if the location of the point where the measurement of stress has to be carried out. This carries the information why it has to be carried out there because that is our point of interest where the something is peaking, either displacement or stress. Something is very high over there. What is the mark weighted distribution between MCQ, box question, etc. in the exam? That I'm not very sure. It will be similar to the assignments. MCQ, MSQ, and box. What is a box question? I'm not sure what is a box question. Okay, numerical entry type. Yeah. That I can't say because I have not framed the paper actually, but it will follow the similar ratios as given in the assignments, more or less. Yeah, 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 no negative marking. Yeah, yeah. You'll just have to excuse me for 1 minute. I just need to take one call. Excuse me. Okay, so once it says that we already know the point where the measurement of stresses has to be carried out, we would prefer to make much precise measurements using strain gauges. All right. So let us look at this question. The given figure, figure 1, depicts the images of word beam viewed through two different arrangements of a polarizer and analyzer. So basically, we have different arrangements. Essentially, what we are looking at is there is a sheet of beam, there is a sheet with the word beam, and we have put a crystal over it. So the crystal has this property of birefringence, where there will be two refractive indices. So, which are mutually perpendicular. So, essentially, we will be seeing two images, which is what we see here. And by virtue of both being mutually perpendicular, we can easily cut one of them out by placing a polarizer perpendicular to that, which is what we saw in the first question as well. So, it just says identify the correct orientation of the analyzer in figure 1. So we have the word beam here. So we see this is a sheet with the word beam. Then we have placed a crystal over it. As the question says, figure 1, a word beam viewed through without any optical instrument, viewed through a crystalline medium. Then C is viewed through a crystalline medium and an analyzer that cuts one of the lights. Viewed the same thing, only thing is we have to identify what is the orientation of this analyzer. Now, one thing we can see is clearly the word beam over here and the V beam over these, in between these two. On comparison, we can see that the word beam has shifted. So clearly, these are not the same words. So naturally, the analyzer is not placed this way. Otherwise, we would be seeing the same word here also without any shift. So that's a given that analyzer is not placed like that, which rules out that this cannot be one of the answers and neither can this be one of the answers. Because if we were to place the analyzer here or place the analyzer pointing that way, it is one in the same. Essentially, this would be the plane in which it will allow the light. So now C and D are ruled out. So that only leaves us with A and B. And from the question, if we see the difference between A and B is that the word beam is shifted in A and B with respect to option C, which is consistent with what we want. The difference between A and B is one. In one case, the analyzer is placed this way, and in the other, it is just placed at 180 degrees, which is one and the same. So essentially, here A or B both could be. So if we see here, what we should be putting here is the analyzer can be both ways like that, which is why A or B could be the correct answer. Okay, so this says identify the correct matrix representation for the quarter wave plate whose slow axis is at 135 degrees with the reference x-axis by Jones calculus. Now we know that every optical element will introduce a rotation and a retardation. Will introduce a rotation and a retardation. So when we club both these two together, what we essentially see is that it can be represented by a single matrix that can account for both these effects. So a retarder and a rotator, rather an optical element, can be represented using using the Jones matrix as cos delta by 2 minus I sin delta by 2 cos 2 theta. Right, let me put it here. Yeah. And then we have minus I sin delta by 2 sin 2 theta. We'll have the same thing here as well. And we'll have the same thing here except for one key change that this is minus and this will become plus. So this will become plus. So given any optical element, if we know what is the rotation it brings about and the retardation it brings about, we can just plug these values and we will get a matrix that is representative of that optical element. So when we see for transformations, let us say we have a vector like that. If we go on adding transformations to its left by multiplying it with matrices, finally it will give the orientation of the final vector, which is what essentially we are trying to do here. So with this background, the question says that we want to represent a quarter wave plate whose slow axis is at 135 degrees. So theta is at 135 degrees, and we are saying that it is a quarter wave plate, which implies that the retardation brought about is one wavelength by 4, and one wavelength we know is 2 pi. So the retardation brought about is pi by 2, which is what we have to simply substitute here. So let us go ahead and do that. So for a quarter wave plate at 135 degrees slow axis, it will be, we have cos, this is delta by 2, and delta is, so this delta is the retardation. Retardation is pi by 2 minus I sine pi, sorry, pi by 2. So this will be 4. I hope you understand. This is delta. This is delta by 2. So it will be pi by 2 by 2, which is pi by 4. So it will be cos pi by 4 minus I sine pi by 4 cos 2 theta. Theta is 135. So 2 theta will be 270. And mind you, here one I'm substituting it in radian, other one I'm substituting it in degrees. So please don't get confused. In fact, why don't I? So 135 by 180. So this will be 3 pi by 4, actually speaking. In radians, this will be 3 pi by 4. So we can all substitute that in consistent units to avoid confusion and mistakes. So this will be cos 3 pi by 4 into 2, because it is 2 theta. So 3 pi by 2. So we know this will be the same here, except this will become plus, and then we'll have here minus I sine delta by 2, which is pi by 4, and sine of 3 pi by 2. And we have the same thing here. We have the same thing here. Okay, so what does this come out to be? We know cos pi by 4 is 1 by root 2 minus I. So we have pi by 2. Any odd multiple of pi by 2, cos pi by 2 will be 0. So cos 3 pi by 2 also is 0. Essentially, it is cos 270, which is 0. We know. So this is 1 minus 0. And then this will be minus I. If cos is 0, sine will be its full this thing. So sine 3 pi by 2 is actually minus 1. So this is minus 1. And this along with that minus 1 becomes plus. So plus 1 by root 2. I into 1 by root 2. Or rather, I should say it is plus I by root 2. So this will be the same here. And this will be the same, except this becomes plus, but it doesn't mean anything since the other part is 0. So what does this give us? 1 by root 2. If I were to take it common, it gives me 1, 1, 1, and 1. So this is the representation of a quarter wave plate using Jones calculus, which has its slow axis oriented at 135 degrees. So let us look at the answers. I'm sorry, this won't be 1, naturally. It will be I. So I hope that is clear. Anyway, so all are positive. So we can see this option B matches correctly. for a quarter wave plate whose slow axis is at 135 degrees. I hope that that is clear. Okay, let us look at this question. It says two discs made of epoxy F sigma is 12 Newton per mm per French and polycarbonate F sigma is 8 Newton per mm per French. So F sigma for epoxy is 12, F sigma for polycarbonate is 8 per mm per French are subjected. So essentially the problem is of a disc. We have taken a disc and we have subjected it to diametral compression like that in photoelastic experiment. The diameter and thickness of both the discs, be it polycarbonate or epoxy, for both the discs, the diameter is 60 mm and the thickness is out of the plane of the screen. That thickness is 6 mm. So thickness is 6 mm. It is given. The load applied is 100 Newton. So we have applied 100 Newton load here. Now it says with this background, just read the following question and answer it. Identify the correct statement or statements regarding the various aspects on the boundary of the disk under diametral compression. The values of the major and minor principal stresses are the same. Now, this is heuristic information. Basically, if we see in the case of a disk, for a disk at the outer boundary, if we see, generally we would be seeing in dark field arrangement, we will be seeing a black color, which implies that the fringe order there is zero. Now, from the stress optic law, outer boundary, the free outer boundary will be will have a fringe order equal to 0. So from stress optic law, we have sigma 1 minus sigma 2 is nf sigma by t, where t is the thickness of the model. So at outer boundary, we have sigma 1 minus sigma 2 is equal to 0 or sigma 1 equal to sigma 2. So at a fringe order 0, we should not directly conclude that the principal stresses are 0. Fringe order 0 only implies that the major and minor principal stresses are equal in nature. So the values of the major and minor principal stresses are same. This we have to know from the mechanics of the problem itself. The stress vector is 0 at the boundaries except the loading points. That is, except these 2 points. Except these 2 points. Everywhere if we see, for a surface, it is characterized by its outward normal. This is the outward normal. Now, what is the traction? This entire surface from here to here and from here to here, except the loading point, it is all traction free. If it is traction free, it implies that the stress vector is 0. So, this holds. Principal stress directions are constants. This is not true. If we were to see how the isoclinics look, for 0 degrees, isoclinics look like that. and then we slowly rotate and sweep the entire plane for 30 degrees and 45 degrees, 90 degrees. It is shown in the lecture how it varies. So principal stress directions are not constants along the boundary. All the planes passing through the point or the boundary, all the planes passing through any point or on the boundary of the disk are principal planes. Now, why is this? If sigma 1 is equal to sigma 2, so essentially this implies if I draw the Moore circle for this, so if I were to draw the Moore circle here, the radius of the Moore circle is sigma 1 minus sigma 2 by 2. So from this, I can follow that the radius is 0, and essentially this would just be a point on the Morse plane, which means this is something like a hydrostatic tension or hydrostatic compression, which is why all the principal planes, all the planes passing through this are 0. So I hope that is clear. So the fringe order at the boundary of the disk would be, as we have already seen from the physics of the problem, it comes that the fringe order would be 0. And experimentally, the fringes are actually shown in the lecture, so you can refer that. If the fringe order at a particular point on the epoxy disk, now we are no longer talking about the boundary, we are going somewhere inside the model. It says if the fringe order n at a particular point on the epoxy disk is 1.5. So let us say that we have considered this point. We have considered a point like that, and here n epoxy is 1.5. What would be the fringe order at the same point in the polycarbonate disk is what is asked. So let us go ahead and look at this a little closely. So this we know. I'll just take this here. Let this be here. Now again from stress optic law, I know sigma 1 minus sigma 2 is n f sigma by t. Now in the case of planar models, these stresses are not affected by elastic constants. Now what does this mean? That if I were to take two disks, one made of another material, and if I were to apply the same load, if I subject these two to the same load, the stresses developed in both the disks are same. So this tells me that stress in one is equal to stress in two. Now this can be counterintuitive to absorb. Essentially, we generally have the notion that when we press two models, let us say one is of a very soft material like rubber, one is made of metal. If we apply the same kind of load, we generally think that the stresses would be more in the aluminum metal disc as compared to the rubber disc, or the other way around. We depending on how we orient our this thing. What we must note is the strains and the displacements are not the same, but essentially stresses are always the same in both these discs. Strain, let me also write that. Strain in one is not equal to strain in two. So we would see one deforming more than the other for the same load. However, stresses that are developed still remain the same for a planar condition. In this case, with this background, if we were to see here, that in the epoxy disk at this point, some sigma 1 minus sigma 2 has caused the fringe order to be 1.5. So sigma 1 minus sigma 2 in epoxy has given me the fringe order F sigma E by T of E, where the E subscript E implies epoxy. Now let me just make a copy of this, bring it here. Next, I conduct the same experiment on the polycarbonate disk. So I have sigma 1 polycarbonate minus sigma 2 polycarbonate at that point is equal to N in polycarbonate into F sigma of polycarbonate divided by the thickness of P. Now I know from my previous discussion that stress developed in both the models are same. So essentially the left hand side of these two equations are same, which implies, so this implies that this is equal to this. So therefore this is equal to this. And we have already been told that both the discs have the same thickness of 6 mm. The diameter and thickness of both the discs are 60 mm and 6 mm respectively. Hence, we can clearly see from here that only this remains because the thicknesses get cancelled out. So from here, we know N in epoxy developed is 1.5 from the question, and N of F sigma of epoxy is given to be 12. We want to find out what is N in polycarbonate, which has an F sigma of 8. So from here, it is easily, we can see that the fringe order that would develop in polycarbonate would be 2.25 at the same point for the same load and same dimensions. So this gives us a very interesting point to take note of is that for the same stress, the fringe order won't be different, won't be same because the material is different. The fringe order at this point, which it was 1.5 in the case of epoxy, now it has shot up to 2.25. So lower my F sigma, more number of fringes I will be able to get. Higher my F sigma, less number of fringes I'll be able to get. So if I were to use the same problem, only I replace epoxy with maybe glass, which has a very high F sigma. For this load, essentially, I will be able to see no fringes. Very feeble response would be there. So the fringe order at this point will be somewhere around zero point 0.1 or so. So I hope this is clear to you. Okay, so let us take a look at this question. Yeah. Different circular polariscope arrangements are given in the table. Identify the background as dark and bright. So what we are saying here is we have a light source again, and then we have the light path like that. We have a polarizer, following which we have a quarter wave plate. Say this is at an angle theta. Now the next arrangement would be the quarter wave plate but kept at some arbitrary angle. Essentially this would be theta plus pi by 2. We generally keep it crossed so that the quarter wave plate mismatch error minimizes. And then we have the analyzer. Then we have the analyzer here. This is the polarizer. This is quarter wave plate 1. This is quarter wave plate 2. Now what is asked? Generally we will be having the model here in between these two and we will conduct the experiment. But Presently, what we have been asked is this is the setup that we have. There is light coming in from here. After this, it becomes linearly polarized. After this, it becomes circularly polarized. Then again, it becomes linearly polarized because the quarter wave plates are kept crossed here. And then light would either get cut off or some intensity would pass through the analyzer. What we have been asked is if we follow these specific combinations of quarter wave plates being parallel and the polarizer being crossed, how to go about identifying whether this will be a bright field or dark field. One way, obvious way to do it is conduct an experiment and find it out. But we would rather go to Jones calculus and easily we can find this out. So I'll just solve this for one example case here. So let the input light be some intensity k e I omega t. I don't have to expand this. This is some light intensity that is coming from here. Let that be the same. My idea is only to see whether it will get transmitted, in which case it will be a bright field. If it gets cut totally, it will be a dark field. So my final output intensity, is it this or zero, is what is the question. If it is the same, unaltered, then it is bright field. If it is reducing to zero, it is dark field. So I won't be able to see any background light under this arrangement. So let us look at the first combination. It says the analyzer, polarizer and analyzer are crossed and quarter wave plates are parallel. Okay. So for the sake of convenience, let me assume that quarter wave plate is kept at, let us say, 45 degrees. The slow axis of the quarter wave plate, I am assuming it to be kept at 45 degrees. Now one might ask the question why we are assuming this. Can't we not solve it without assuming? We can. Only thing is we will have to do longer multiplications which will become obvious in the course of the explanation now. So, and let me also assume that polarizer P is at 90 degree. So for this figure, if I were to write light intensity, so how will I go about writing it? First, I have the actual light. So let me draw a line like that to demarcate the screen. Yeah. So I have k e I omega t. This is the light that was emitted from the light source. Now I have the polarizer. I have assumed that it is at 90 degree. So how can I represent that using a vector? 0, comma 1. What does this imply? X component is 0, Y component is 1. So this two together forms these two together. So whatever comes out of this is what is coming out of the polarizer. What will come out of this? 0 k e I omega t, which implies that all the light is coming parallel to the y axis. So that is what this is. So this is the light source. This is the polarizer I have accounted for. Now comes the first quarter wave plate. I have made an assumption that it is kept at 45 degrees. In fact, let me refine the assumption and take it to be 135 degrees. Why? Because we have already calculated in one of the questions the expression, this expression for a quarter wave plate which is kept at 135 degrees. So I can directly make use of this. Otherwise, I would have to represent the matrix like this and multiply it out, which will towards the end it will get cancelled. But nonetheless, I will have to multiply this out, which I'm trying to avoid. That is why I'm I assume that we are keeping that at 45 or 135 degrees to simplify the thing. Because our idea here is just to see whether it is bright field or dark field. I hope that is clear. So I'll come here, I'll paste it here. Let me remove this. Let me remove this. So I have placed the first quarter wave plate here. Now these three together form what is the output light intensity from this component. Now comes the second quarter wave plate. And in our question, the first part, we are saying that these are kept parallel, which means the same thing I have to repeat it again. Multiply that again without any change because it is kept parallel. And then I have the analyzer. So for the sake of explanation, I'll just move the entire thing here. Now I have the analyzer. Now since in the question it is said that polarizer and analyzer are crossed, and I have already assumed the polarizer to be 90 degrees. So it clearly implies that my analyzer is at 0 degrees. So what is the light vector that comes out is what we are trying to see. So this actually the light vector, analyzer which is at beta degrees with the horizontal is given by cos beta sin beta minus sin beta and cos beta. So I have to substitute beta equal to 0 here. So this will give me cos 0 is 1, sin 0 is 0, minus sin 0 is 0, and this is again 1. When I multiply this with this matrix, it gives me the output light intensity along beta and output light intensity along beta plus pi by 2. My analyzer is at beta, which is 0. So this entire multiplication will actually give me a vector. And I have to read out the x component of that vector to find out what is the output light that is coming. So it is as simple as that. So let us go ahead and multiply this out for the first case. What I'll do, I'll take this 1 by 2 and I'll take this 1 by 2, multiply both. So root 2 squared is just 2. I'll just put 2 here. So that is accounted for. Let me keep this thing unchanged. So if I multiply these two things out, what do I get? 1 into 0 plus I into 1, and then this gives me 1. So this I have to multiply with this matrix and then multiply it with this matrix. So this is what the product gives me. I hope that is clear. So let us further multiply this out. So this gives me 1 by 2. In fact, let me take this component as it is, bring it down, and then let us multiply these two things out. So this gives us what? I plus I, and this gives me I squared plus 1. Now we know I is root over minus 1. So I squared is minus 1. So if this is minus 1, this is minus 1 plus 1. So this goes to 0. This goes to 2i. So this comes out to be 1 by 2 into 1, 0, 0, 1 into 2i and 0. So let us further multiply this out. This is 1 by 2 into 2i, and this is 0, 0 totally. Okay, is the I and this is 1. Okay, I plus I. Yeah, so this gives me I and 0. And let us not forget, we'll have K E I omega t. So when we multiply this out, if we are looking at the first component, when we multiply this out, if you are looking at the first component, if we multiply this out, the real component will be non-zero. So we can see that there is some light intensity that is coming out of the analyzer when it is kept like this. So when polarizers are kept crossed and quarter wave plates are kept parallel to each other, the light passes. So essentially it will be bright field. So similarly, one can also try out for other combinations. I encourage you to do that. I hope this is clear. So we can see that instead of performing an actual experiment, we can use Jones calculus to our advantage by the fact that we can represent any optical element that brings about a rotation and a retardation. We can represent that using using a matrix and go about solving the problem. So I hope that is clear. Okay. So yeah. So let us take a look at this question. It says at a point P in a photoelastic material. Just a moment. Yeah, at a point P in a photoelastic material, the fringe order 5 was obtained. So there is some photoelastic material and it was subjected to some problem, some mechanical loading, and the fringe order was 5. N is equal to 5. Okay. The isoclinic parameter at this point was 30 degrees. So we know isoclinic represents the maximum principal stress direction or the principal stress direction, I should say. So that comes out to be 30 degrees is what it says. The material stress fringe value for the model material is 8. So we can know that it is some kind of a polycarbonate per fringe. F sigma is given. The Young's modulus, the model materials Young's modulus is E is 2.6 GPa and the Poisson's ratio is 0.28. All this is given. Before the application of loads, the thickness of the model was 6 mm. So the thickness of the model is 6 mm. And then after we applied the load at this particular point P, the thickness was measured using a lateral extensometer and the thickness T1 is 6.01. So what has happened essentially we had some model at point P we were looking it was subjected to some load. After the out of plane thickness was 6 mm. After the application of the loads, it was measured that at this point the thickness became 6.01 mm. Very well. So these quantities are asked. So let us see how to address this. So we know that again from stress optic law, we know sigma 1 minus sigma 2 is n f sigma by t, the thickness of the model. So this implies, so let us draw the Mohr circle. For a general case of a Mohr circle, if This is my Mohr circle. I'm assuming that sigma 1 and sigma 2 are positive, but that doesn't make much of a difference. Even if it were the other way around, the mathematics will finally lead you to the correct answer. So if this is sigma 1 and this is sigma 2, so photoelasticity basically gives me from the stress optic law, sigma 1 minus sigma 2, I can find out. If I measure the fringe order, if I know the material stress fringe value and thickness, essentially it has given me the diameter of that Mohr circle already. But the question asks, okay, the question first asks, what is sigma 1 minus sigma 2 in MPa? So let us go ahead and find that out. So what is this quantity? Sigma 1 minus sigma 2 is N is 5 into 8, 5 into 8 by 6. So 40 by 6 is what our sigma 1 minus sigma 2 is. So this is 6.67 MPa. We have got as sigma 1 minus sigma 2 already. So this we have got. Fine. Now let me actually make this a little bigger for the sake of explanation. Let it be like that. So here I have sigma 1. Here I have sigma 2. Now let us say that there is some generic plane. So from the center of the Mohr circle, if I were to draw the line like that, let us let us say this is sigma x. Now we know from the property of the Mohr circle, if I were to extend it diametrically opposite, I will have sigma y here. This will be sigma y. And this distance, this is tau xy. We know this from our basic strength of materials. So let me just drop an altitude here like that. So let me call this O, let this be A, and let this be B. And again, if this is sigma x, by some rotation, if that takes me to the principal plane, I know how to label this. So this is nothing but 2 theta t. Why? Because in the Mohr circle, when the rotation is 2 theta p, in the physical plane, the rotation would be half of that, which will be theta p. I hope that is known. So here, actually, this instead of theta, it is actually theta p. The isoclinic parameter is theta p. Okay. Now we know in triangle OAB, I have the triangle like that. I know this angle is 2 theta p. This distance I can see from here, it is nothing but the radius of the Mohr circle, which is equal to sigma 1 minus sigma 2 by 2. So from here, this is O, this is A, this is B. So therefore, OA is nothing but sigma 1 minus sigma 2 by 2 cos 2 theta p. This is from basic geometry. And AB is nothing but sigma 1 minus sigma 2 by 2 sine 2 theta p. Now we can see from here that this distance AB we can find out like that, and this is nothing but my tau xy. So this is my tau xy. Now what is this distance? This If I were to extend it on this side also, what I would be seeing is essentially these two are similar triangles. So that congruent triangles, in fact. So that implies that this OA is actually half of this distance. And this green distance is nothing but sigma x minus sigma y. So half of that is sigma x minus sigma y by 2. So therefore, this is nothing but sigma x minus sigma y by 2. So these things we have found out. Now this we know, theta p we know. So by substitution, we can easily find out what is the difference in the normal stresses. Similarly, by substitution, we can find out what is the shear stress. So using photoelasticity alone and our knowledge of Mohr circle, we are in a position to find out what is the difference in the normal stresses and the actual shear stress. We have not been able to separate out sigma x and sigma y yet. We have simply found out sigma x minus sigma y. That quantity we have found out. So let us go ahead and evaluate that. So sigma x minus sigma y is nothing but sigma 1 minus sigma 2 by 2 cos 2 theta t. Now we have already got this quantity sigma 1 minus sigma 2 as 6 point something, 6.67 by 2 cos of 2 into theta p was given to be 30 degrees. So this is 30, which is cos 60. So 6.67 by 2 into cos 60. We have got this as 1.67 MPa. Very well. I hope the calculations are okay. I encourage you to check that along with me. Anyway, by 2 into cos 2 theta p. Yeah, 5 by 3. Some see, looks okay. Tau xy is sigma 1 minus sigma 2 by 2 sine 2 theta p, which is 6.67 by 2 sine 2 into 30. So 40 by 6 by 2 into sine 2 into 30 gives me 0.348 MPa. Okay, so we have got these two quantities. We've got these two quantities. So let us report that 1.67, 0.348. So this came out to be 6.67 MPa. Difference in the normal stresses comes out to be, what was it? 1.67. This is 0.348 MPa. Now we have been asked to find what is sigma x, that is the separated stress. What is sigma x is what we have been asked to find, and also sigma y. We have to separately find that. Okay, so another information is given in the question that this is the material property. Initially, it was having a thickness of 6 mm. Then when we loaded it at that point P, the thickness became 6.01. So how do we use this information now? Now we know for any material, or rather from Hooke's law, excuse me, my screen is getting a little stuck. Yeah, so from Hooke's law, so the strain in the z direction is given by sigma in the z direction by E minus mu sigma x by E minus mu sigma y by E. This we know, and it will go cyclically in x, y, and z, so that all the strain components are known from the stress components. Now for the present problem, it's in plane stress. So therefore, sigma z is 0. So therefore, epsilon z is nothing but minus mu by E into sigma x plus sigma y. So far, so good. Now, do we know anything about epsilon z? Epsilon z is nothing but change in the thickness. That is the final thickness 6.01 minus the original thickness divided by the original thickness. This is my epsilon z essentially. It's nothing but minus what is mu. Mu is given to be 0.28 and this is 2.6 GPa minus 0.28 upon 2.6 E3. In MPa I am writing E3 into sigma x plus sigma y. So if I were to solve this, I get sigma x plus sigma y is equal to what? 6.01 minus 6 divided by 6 into 2.6 E3 divided by minus 0.28. So this comes out to be minus 15.476. Units will be MPa actually. Now, let me just cross check the calculation once again. But in any case, I encourage you to solve it together so that it becomes clear for you. Okay. So this we have got by virtue of this information that how the thickness changed and the material properties, we have been able to find what is the sum of the normal stresses there. And from our Mohr circle and photoelasticity, we already know what is the difference there. So when we know sum of two quantities and the difference of those two quantities, we can easily find out what those individual quantities are. So sigma x minus sigma y is nothing but how much we got this 1.67. So we know the sum, we know the difference. Call it equation 1, call this equation 2. So if we were to add 1 plus 2, or rather I won't do that. What I can do is I can just express this as a matrix. So this is 1, 1, 1 and minus 1 into sigma x, sigma y gives me minus 15.476 and this is 1.67. So therefore, sigma x and sigma y is nothing but 1, 1, 1 and minus 1, the inverse of this matrix into minus 15.476 and 1.67. If you are not at liberty to have a matrix calculator, you can always add these to simple elimination as we have been doing from our high school. So I hope that is clear. Yeah. So for the sake of completeness, I'll just solve this also. This be 1 and this is minus 1, 2 and 6, minus 15.476, 1.67. A inverse into B. This gives me minus 1.15. This gives me minus 14.32. I encourage you to check the calculations. Anyway, my idea is just to convey on how to solve the problems. With better practice, I encourage you to have calculated this parallelly. so that things become clear. Because my focus is more on the conceptual development. I hope you can bear with that. Very well. Okay. So we saw in this problem, what have we learned? That in conjunction with photoelasticity, with a photoelastic experiment, if we can somehow measure the out of plane displacement, then we are in a position to separate out the stresses instead of just having sigma x minus sigma y or sigma 1 minus sigma 2. We are able to calculate the individual stress components. But it is important that it is at that point P. What we have found is at that point P. If there is a model, we have found at that point P, because that is where the thickness became 6.01. It is not necessary that everywhere it will be 6.01. So that is what is to be kept in mind. Okay. So let us look at this question. It says the expression for the principal stress difference sigma 1 minus sigma 2 at the center of a circular disk under diametral compression is which of the following? Actually, this is more like, if we familiarize ourselves with photoelasticity, we will be seeing that in transmission photoelasticity, the disk under diametral compression is the most favorite problem that we take for calibration, which is why, in a sense, this question is asked. If we have the diameter as d, if we have the out of plane thickness as h, and if we have the load applied as p, so sigma 1 minus sigma 2 comes out to be 8p by pi d h. This is from theory. Essentially, for a disk under diametral compression, we have a big expression for sigma x, sigma y, and tau xy. So we can calculate sigma x, sigma 1 from those expressions. We can also calculate sigma 2 from those expressions, take the difference, and so this will have x squared, y squared, and so on. There will be big expressions. For a disk under diametral compression, the origin is set at the center of the disk, and we have been asked what is this at the center point. So what do we have to substitute? We have to substitute x equal to 0, y equal to 0. It will water down to a simple expression such as this. This is from theory. From an experiment, we know sigma 1 minus sigma 2 is n f sigma by h. So therefore, n f sigma by h is 8p by pi d h. So these two things cancel out, or f sigma is nothing but 8p by pi d n. So this actually tells me that this is some constant k into p by n. That constant is set 8 by pi d. It is a constant once diameter is set. So this expression, what we generally do is we'll take a disk, because this f sigma is a very important parameter to link our mechanics to optics that we are visualizing for our stress analysis. So when we generally get a photoelastic sheet, we'll cut out a disk of a known diameter. We will load it with a known load. At the center, using compensation techniques, we can find out what is n. So what we'll do, we will plot p versus n. Let this be p and let this be the fringe order. So let us say that we apply 2 kgs and the n at the center, it went to some point 0.1, whatever, some value. Then we increased p, we got a higher n. So there will be data that we will plot like that. So essentially what we are plotting is p versus n. If we take a least squares best fit line here, and the slope of that will give me p by n. Once I get that p by n, I just have to multiply it with this constant, which is 8 by pi d. I have cut the disk out of a known diameter. That d I substitute. So this quantity, with using this quantity, I can actually find out f sigma for that disk. There will be a sheet like this, out of which I have cut this portion out. The remaining portion is still intact. I can cut some model out, conduct my photoelastic experiment. For that, I can take the F sigma that I calculated here. This is the entire purpose of this calibration. And this we are using only one point to do this. So this is called one point photoelastic calibration where we use the center point of the disk. There are also ways and means to collect it along the fringes. Take some 40 points, which is the sample least squares method, which is also discussed in the lecture. But actually speaking, this question only asks what is the expression. But there is no point in just knowing the expression. I just wanted to elaborate on why it is asked and what was the use behind knowing this problem. So I hope that is clear as to why we do this and why calibration is important. It will be the best fit line, which is what will give this. Okay, so far we have seen everything to do with transmission photoelasticity. Now coming to the analysis, there are different types of analysis that we can do in order to find out the fringes. Generally, there was conventional photoelasticity where people were finding the stress at one point by doing the compensation. Whereas now we replace a human eye with an electronic eye, which is nothing but a camera. We generally capture the image. For example, this image that we see here. I'm sorry, my screen is stuck. Just give me a minute. Yeah, this is a this is quarter of a disc actually. It's an experiment done on an entire disc, and this is experimentally captured. This is a photoelastic experiment, photograph captured from that. And it says RGB values at the points can be used to determine the fringe order n. A disk is subjected to diametral compression with a load of 700 Newton. The diameter and the thickness are so and so. The RGB value and the coordinates of 2 points. Basically, in this problem, we have taken 2 points, A and B. Our interest is to find out what is the fringe order exactly at that point. Also, the grayscale representation for the total fringe order evaluated using the least squares technique is given. So, for this point A, we have already seen that our origin will be here at the center of the disk. This is X and Y. So, for this point A, we have 21 mm like that, and A and B. Okay, maybe X and Y is flipped, but regardless, maybe they have taken some random values. But that is besides the point. What we are trying to say is at that point A, RGB, we have captured an image. That image is a color image. So any color image can be decomposed into three basic planes, red, green, and blue. And it will have integers representing the intensities. So for point A, at that point, red intensity is 145, green is 127, and blue is 200. So when we have a combination of this, it gives the color at that point, the fringe color at that point. Same thing applies for B. From a known problem, we have already generated a calibration table. What does the calibration table tell us? That at a point, if red is 165, green is 130, and blue is 156, the fringe order there is 1.8. Similarly, we have got the entire table like this. This will be much longer. Only an extract out of that table is given here. This will be much longer. This has only 6 entries. In general, we might be, depending on our resolution, we might be having hundreds or thousands of entries. Okay, so now we know that our RGB at the point is 145, 127, and 200. We are able to see that it exactly doesn't sit for any of these. So naturally, the fringe order has some difference. It is not exactly sitting. So what is the minimum least squares computed at A is what is asked. So what is the error? Least squares error is given by root over R, uh, R specimen minus R calibration squared plus G specimen G calibration squared plus B B calibration squared. So this is our least squares error essentially. Now it is asking where will it be the minimum. So if we were to plot, it will have some plot like that. We will see which is the minima, assign the fringe order over there. That is the idea behind this. So you can easily calculate that. For the first case, I'll just calculate the difference. So I can see RS minus RC. This minus 145 is what we are trying to see, or 145 minus this. 165 is minus 20. I'll have GS minus GC and DS minus BC. Now, if 20 entries are given, it doesn't mean that a person has to do 20 calculations. That is where we should intelligently gauge where it is looking similar and only account for those rows and be done with it. Otherwise, it is just a mechanical process which we can do it by Excel. So this is minus 20 for point A. This is for point A that we are seeing. So 127 minus 130 is minus 3. 200 minus 156 is 44. Similarly, we can populate these values. In the interest of time, I'm not doing that right now, but you can get some practice by doing that. Based on these three values, essentially why we are doing least squares error is so that this doesn't get nullified by this. All the errors are accounted for their absolute values, and then towards the end we take the root over so that it is representative of the actual error and nothing is getting cancelled out. That is the very idea behind the least squares error. So based on this, we will see where the least error comes and assign that fringe order to point A. So this is what is the theory behind this. But in the interest of time, since we have just reached digital photoelasticity, we still have to go to look at some problems from photoelastic coating, brittle coatings, and strain gauges. I'll move on. I hope that this is clear. This we have already solved in one of the live sessions, so you can just try it out on your own. Okay, so now the question says we have moved to photoelastic coatings. Till now, we were seeing transparent materials which were birefringent, and that was transmission photoelasticity. This is to do with photoelastic coatings. A tractor tire needs to be studied. So this is a tire is made of rubber. Needs to be studied using photoelastic coating techniques for the stresses developed. Mithila selected a suitable coating material from the given list below. The calibration was done with a 2 mm. So the thickness is 2 mm. We have a yeah. So we have a tension specimen where we have applied some tension like that, and its thickness is 2 mm is what is given. So this was used for the calibration. That is, we pull, we find out what is the fringe order. 2 mm made of a coating material using transmission photoelasticity under white light with a wavelength of 577 nanometers. The calibration specimen had a width. So this width is 30 mm and a length of 70 mm. This is 70 mm. During calibration, a fringe order of 3.5 was observed for a particular point when the load was 600. So when the load was 600 Newton, we know that sufficiently away from the loading points for a specimen under uniaxial tension, every point has the same direction of principal stress, and the principal stress is along this direction. The other principal stress is zero. There is only uniaxial tension. So sigma 1 here is nothing but my stress, that is load by area. Load is 600. What is area? 30 into the thickness, which is 2. So this is my sigma 1 divided by 30 by 2 is 10 MPa. Sigma 2 is 0 because this is uniaxial tension. And we got the fringe order. It says fringe order was 3.5 at this particular point. So sigma 1 minus sigma 2, which is nothing but 10, was equal to 3.5 F sigma by the thickness. What is the thickness? It is again 2 mm. So therefore, F sigma was 20 by 3.5. So F sigma for this material is 5.714 Newton per mm per fringe. So I have got the material stress fringe value for this. Actually speaking, the question asks, we have a range of materials that are available, which is suitable for the coating is what is asked. So what goes into the selection? The main thing is that the coating should not participate in load sharing. Why? Because if we are trying to analyze that tire and we put a coating that is equally strong, it will also participate in load sharing, which means that load taken by that tire will be much lesser, which is not we are trying to study. So there should be no reinforcement effect from the coating onto the specimen. It should be as less stiff as possible, as flexible as possible. Which is why if we see E here, E is the least for polycarbonate, polyurethane. So polyurethane makes for the ideal choice for studying this rubber material. So we'll go ahead with polyurethane. For that, they conducted such a test and they loaded the uniaxial tension specimen to 600 Newton and they found that the fringe order was 3.5. From this analysis, we found out that F sigma is coming out to be 5.714 for this case. Newton per mm per fringe. Now this is F sigma, but our main focus in photoelastic coating, which is strain based, is that the strains get delivered faithfully. So we essentially need the material strain fringe value. Now we know that there is a relation between F sigma and F epsilon, which is given by 1 plus mu E, mu C, which is the mu of the coating, divided by EC into F sigma. And this we have clearly derived in one of the sessions. I have spent much time in deriving this, is also given in the lecture. So you can just revisit that. I don't want to derive that right now. I've already derived it, so you can take a look at that particular week. So F epsilon, if I were to calculate this, the coating, we are going with polyurethane. So E is 0.004 GPa, essentially 4 MPa. Mu C is 0.5. So let us go ahead and calculate F epsilon. So what does this come out to be? This is 1.5 divided by 4 MPa into 5.714. So F epsilon comes out to be into 1.5 by 4 is 2.418. 2.148, sorry. 1428 mm per inch. This is just from dimensional analysis. So what is the strain optic coefficient? Strain optic coefficient is given by K, which is equal to lambda by F epsilon. In general, when we use photoelastic coating, there are two ways to find out how to calibrate the material. One is we paste the coating to a cantilever beam, load it, find out K, and from this expression find out F sigma. That is one way to do it. Another way to do it is by what we have done in this question. We take the coating material, we pull it, we actually find out F sigma. From F sigma, we back calculate the F epsilon using this expression which we have derived earlier. So from here, it follows that K is lambda by F epsilon. So we can just calculate this quickly. This is 577 nanometers, which is 10 power minus 9 meters into 10 power 3 millimeters, because this quantity is in mm, so we should be able to substitute that correctly, consistently. F epsilon is 2.1428. So what does this come out to be? In the question, it's, excuse me, there's some issue with my screen. In the question itself, it says, report your answer in 10 power minus 4. So let us calculate this into 577 10 power minus 9 into 10 power 3. So 2.69 is what I'm getting. 577 by 2.1428 is 2.69. E minus 4 fringe is what I'm getting. So we should report it as 2.69 because this is already given in the question. So while answering, please answer the question carefully after seeing what is asked in the question. Okay, so let us move on to this question quickly. A calibration test was done before using a brittle coating on a landing gear of an aircraft. A cantilever beam of aluminium, epsilon, 1 minute, a cantilever beam of aluminium with these material properties was used for calibration, and the threshold strain was found to be 600 microstrain. The material property for the coating are EC something and E mu C something. So what is the failure stress is what is asked. So let us see this question. Excuse me, just a moment. Excuse me. Yeah. So for a coating, we know that the photoelastic coating analysis is done on the assumption that strain in the coating is strain in the specimen is equal to strain in the coating. This is the fundamental assumption behind the photoelastic coating techniques, or rather any coating technique for that matter, be it brittle coating or photoelastic coating. We see that once we paste the coating, it is faithfully bonded onto the specimen such that strains from the specimen, so surface strain of the specimen is delivered faithfully to the coating material. So from this follows that epsilon 1 S is equal to epsilon 1 C and epsilon 2 S is equal to epsilon 2 C, where S is the specimen and C is the coating. So there is a long derivation for this where we generally first write the coating stresses, coating strains in terms of coating stresses, and then using this expression, we find out what the coating stresses would be in terms of the coating, in terms of the specimen stresses. But I'm not going through that derivation since I've already done it twice at least in the previous session. So you can just take a look at that video. In the meantime, let us see what the final expression comes out to be. So sigma 1c, we get it as EC upon ES into 1 minus mu c squared into sigma 1s 1 minus mu c mu s plus sigma 2s into mu c minus mu s. So we get this for sigma 1s. If I just copy this for sigma 2s, I just need to replace this. Sigma 2s, this position will change. It will come here and this will go here. This will go here. That is all the difference there is to it. Now, what we have here is we have the specimen stresses and the coating stresses. In the case of a calibration specimen, which we have initially done, they have said that they used a cantilever aluminum beam of these properties to do the calibration and found that the threshold strain was 600 microstrain. So the brittle coating essentially cracked at 600 microstrain. So what would have so the question asks what is the failure stress in the coating in MPa? So for the calibration specimen, we have used a a cantilever beam, which implies that sigma 2s is essentially 0 because the top fiber is under uniaxial tension and the threshold strain was found to be 600 microstrain. 600 microstrain, yes. So sigma 1c from here, if I just omit sigma 2c part, sigma 2s part, I only get this quantity left. So from here, if I take sigma 1s outside and es outside here, this is one and the same as that expression. And at failure, I know this is nothing but my, at failure, it is nothing but my sigma threshold, which is stress by strain. So that is all there is to it. So from here, and since we are referring it to as failure, so we will replace it by sigma naught. So that is the only difference here. So therefore, sigma naught C is nothing but EC upon 1 minus mu C squared into 1 minus mu C mu S into epsilon threshold. So let us quickly substitute what the values are. We have been given EC as 1.45 GPa divided by 1 minus mu C is given to be, let me just check it from the question once. Mu C is 0.42, mu A is 0.33. Now we should not get confused that this is mu S and that is mu A. Essentially, this implies that it is for the specimen. And since we are dealing with calibration presently, the specimen was aluminium. So mu C is nothing but mu A. I hope that is clear. So this is 0.42 squared into 1 minus 0.42 into 0.33. This entire thing into the threshold strain, which is 600 microstrain. So what does this come out to be? 1.45. Let us solve this quickly. divided by 1 minus 0.42 squared into 600 e minus 6. So this comes out to be 0.91 MPa nearly. So the stress in the coating at which it failed is 0.91 MPa. If the material of the landing gear was aluminium, the specimen stress to cause this coating to fail would be what? Is what is asked. So from here we know that I'll just add one more page here. So what is asked is what is sigma 1 S when the coating failed. So this is nothing but 0.91 is I know that this is that is what we are trying to find out is we have this expression. I'll again take this expression, take it here. We know we know this quantity at failure is sigma naught s. We are just trying to back calculate sigma 1s from here. So this comes out to be into, yeah, so this will be sigma 1s. Now this is so because the question says that let the landing gear also be of the material sigma 1s. In such a case, what would the specimen stress be when the coating fails? So there is no mismatch. Essentially, there is no mismatch between what the calibration on what metal the calibration was done and what metal the landing gear is made of. If it happens to be a different material, then there would be a mismatch that we need to account for, which is discussed in one of the problems discussed earlier. So I won't delve much into this because we are running out of time and I want to cover some more ground and at least cover the problems that I've taken up today. So you can take a look at these derivations afresh, which was done in detail in the lectures and try to address this problem. Essentially, once this is derived, rest is just a matter of substitution of these values. So I hope you can bear with that. So I'll move on to the next problem. There are a couple of more problems which I want to discuss before we discuss today. So I'll move on. Okay. So this question, it's an interesting question. What it says is this is the isoentalpic data. So essentially, we have some model over which we have pasted a brittle coating, and then we start loading the model. Once we start loading, cracks develop. So cracks would have developed like that. So what the experimentalist did is he mapped all the tips of the crack when the load was 300 Newton. Then they started increasing the load again. They went till 400. The cracks which were here, now they progressed to this point. So he again mapped all the crack tips, connected all the crack tips. So this is known as isostatics. So essentially, once this was done till the load was increased to 1500 Newton. And this is the data that we have. Now it is given in the question that the material over which this brittle coating was applied is actually steel with E is 210 GPa and mu as 0.28. And the threshold strain, the brittle coating will crack when its strain will reach a maximum strain. That threshold strain is given to be 450 microstrain for this problem, whatever brittle coating was used. Now the question says the stress in the specimen when this first crack appeared was what? Is what is asked. So from here we know, excuse me, just a moment. Yeah. So we know that the first crack appeared when the load was this. So what was the stress in the specimen? What would have been the stress is the strains are getting faithfully transmitted. So the stress would be nothing but E into epsilon threshold, which is 210 GPa into 450 microstrain, which is 10 power 3. So essentially it will be 94.5 MPa. So this was the stress when the first crack appeared. And the first crack appeared at a load of 300. Even as per the pattern, we can see that the load was 300 Newton. The load applied was 300 Newton when the first crack appeared. Now, as we progressively load it, this is the peak load zone because the first crack appeared from here. As we go on loading it, when this reached its peak, naturally the other portions the stress was much less. Now we are loading it beyond that. So the peak, whichever is loaded more, that area also keeps on increasing. That is why the cracks are progressing. So now this says that the maximum stress when the load has reached 1000 newtons is what? That is now the crack has initially the crack was here. That crack has now progressed and reached this point. What is the maximum stress? Is what is asked. And what is the minimum stress is what is asked. So we must understand one thing that maximum stress when the crack would have reached would be at this point because this was the initial stress concentration zone. We kept on loading it till the crack which was here has now gone till this point. So the maximum stress is occurring here. Where is the minimum stress occurring? Minimum stress is occurring at this point because the in the context of the brittle coating, it has just cracked over here. If we increase our load to 1500, the crack would progress like that, and the minimum stress would be here as compared to the maximum stress over here. So this we can do a linear interpolation because we are living within the linear elastic domain. So the stress 94.5 has to be scaled by this 94.5 was for a load of 300 newtons, but we are looking at what is the load when the load has what was the stress when the load has reached 1000 newtons. That is all we are doing. So this would come to 315 MPa. Minimum naturally would be the same as our threshold because this is where we started with. The crack has reached only this point. So this is where the stress has just reached the bare minimum for our specimen to crack, which happens to be 94.5, which happens to be 94.5. Other way to look at this is I can take this to be 1000 by my reference load of 1000. So this is 94.5 MPa. So I hope, so this is an interesting question in the sense that using a graphical representation, we can find how the crack tip would have progressed from time to time. At the same time, if we were to know the material values at those time intervals, we are also in a position to evaluate what our specimen stress would have been. This is explained for one of the problems in the lecture. So I encourage you to go through that. Okay, so we have reached our strain gauges. I'll just take 2 to 5 more minutes. I'll just quickly explain this. A strain gauge was used to measure axial strain developed in the calibration experiment of cantilever beam. The strain was connected to one of the arms shown in the figure. So this is given. What should be the resistance in ohms in order to make the bridge to balance and increase the bridge sensitivity and have the strain gauge if the strain gauge resistance is 350 ohms. So this is given to be 350 ohms. It is asking what should be these resistance values in order to maximize or rather increase the bridge sensitivity. Now we know M is given by R1 by R2 and there is one expression for the output voltage which is R1 R2 by R1 plus R2 the whole squared into delta R1 by R1 minus delta R2 by R2 plus delta R3 by R3 minus delta R4 by R4. Granted, this is for a case where there are four resistance and all are changing. Whereas in our present case, only one strain gauge is there. Rest are just dummy resistors. So they won't figure in the problem. Essentially, it will be only this portion into the output voltage. So naturally, these quantities will not appear. If we maximize this, which is done in the lecture, if we take M to be 1 R1 by R2 and we rewrite this expression and we maximize this such that dou delta E by dou M equal to 0. If we were to plot this curve, essentially what it says is when M is equal to 1, we have the maximum output. And also for a balanced bridge, R1, R3 is equal to R2, R4. So therefore, R1 by R2 is equal to R4 by R3. So when we maximize this, this says that M equal to 1, that is R1 by R2 equal to 1 is what will give us the maximum output. So R1 should be equal to R2 and from this expression it follows that this ratio should hold. So therefore, this explanation, this justification only serves to prove one point that when we have all the resistors equal to the strain gauge resistance, then we can maximize the signal output. So therefore, R2, 3, 4 should also be 350 ohms in order to increase the bridge sensitivity. Okay, so this question says, taking the voltage supplied by the strain gauge meter as 5 volts. So the voltage supplied is 5 volts. The resistance of the strain gauge changes by 150 micro ohms. So the change in resistance is given to be 150 micro ohms. The output voltage E detected will be what? Now we know this expression. This big expression is there. And this is a quarter bridge arrangement. So R2 to R4 is not there. So only these quantities we need to substitute. It is just a simple substitution which we can do. So the output voltage is given by R1 and the question says it is already 350 ohm resistor. So R1 plus sorry R1 R2 R1 R2 by R1 plus R2 into delta R by R into the voltage which is 5 volts. So I'll just quickly solve this. 350 squared by 2 into 350 by 350 into 150 minus 6 into 5 divided by 350. Okay, are we not accounting for something? Delta R by R. R1 R2 squared. Right. Yeah. Yeah, I was wondering why I'm not into 2 squared. divided by 350 into 150 minus 6 into 5 into 10 power 6. So we have been asked to report this in. So this comes to 0.536 microvolts. So whatever answer we get, since we have been asked to report it in, whatever answer we get, since we have been asked to report it in microvolts, we'll multiply it by 10 power 6 and then report it. So this is accounting for the 10 power minus 6. I hope this is clear. So this will be the output voltage when the change in resistance is so much. If this if the gauge factor for this strain gauge is 3, what is the strain measured? Now we know that delta R by R is nothing but Sg epsilon A. Now we have been asked epsilon A when delta R by R divided by Sg. So what is delta R? 150 micro ohms divided by 350 is my resistance divided by 3. So epsilon A comes out to be 150 E minus 6 divided by 350 by 3. And again, we have been asked to, this is to be kept in mind, we have been asked to report it in micro strain, which means we will multiply it by 6, 10 power 6 and report it. 0. Epsilon is 0.1428 microstrain. So I hope those who are taking the exam should read the question carefully as to what units and what is being asked and then report. Because even if someone knows the answer, they should not make an error in reporting the answer correctly because it is computerized checking. So please pay attention to that. I hope that is clear. Okay, so anyway, we have come to the last question. I'll just quickly run through this. I won't solve this fully, but at least that way I'll do some justice to closing the course. So a strain gauge has been selected to determine the strains developed in a tension test on flat specimen. Rajesh visits the vendor, Vishay Micro Measurements, and they have some requirement. Based on these requirements, the question asks which one to select. Now, naturally, this will look Greek and Latin to a person who is not exposed to this, but fortunately, Vishay Micro Measurements already has a designation system where each and every letter or number it means it can be mapped to a particular characteristic of that strain gauge. Depending on the need, he has these five choices alone and which one to select out of these. So I would encourage you to actually go through this question and try it out once because this is just a matter of shortlisting based on these requirements and knowing what it is. So I don't want to delve much on that. I'll just move on to the next sub question. It says that when a strain gauge of 120 ohm is selected, what is the loss percentage loss incurred if Rajesh has lead two copper lead wires for connecting the strain gauge to the meter? Okay. The total resistance of the copper wire is taken to be 1.7. The total resistance. So what this is saying is generally when we have a strain gauge like this, we connect it to the output. We have the output here. We have another arm like that. Same thing goes here. And then same thing comes here. And then these two, we excite this with a voltage. For balancing our bridge, we will initially balance it. Essentially, this resistance will be a strain gauge, in fact. So this is how it will be in a two-wire circuit. Now, what will happen is these lead wires that are connected with the length, if these are just a few millimeters or centimeters long, it won't matter. But if it is too long, because we know that resistance also depends on rho L by A. So if the length is very, very long, then naturally its resistance also will be long. So the cumulative resistance of this arm will no longer be what it is for the strain gauge. It will be a major portion that will be contributed from the lead wires, which will actually not balance these things out. So what will this do? This will essentially throw the bridge off balance, and it is possible we might not be able to initially balance the bridge and bring the output voltage to zero so that no current is passing through the system. So that balance gets affected by this. This is circumvented by suitably modifying. What we do, we generally connect it like that, or rather, what I should say is, generally we will disconnect this and connect it like that. So this is called a three-wire bridge, where if we see one strain gauge and one lead wire, other lead wire and the other dummy resistor gets connected like that. Just by this simple tweak from here to here, from two wire to three wire, we can see that our resistance, uh, our sensitivity of the strain gauge increases in a significant manner. So in such a case, what the question asks is, what is the percentage loss in the signal? Percentage loss in the signal is given by the resistance of the lead wire Okay, well, this brings us to the closure of the course. So today we have discussed right from the starting of experimental techniques to the we went through photoelasticity, transmission, then reflection photoelasticity using photoelastic coatings, followed by our analysis of brittle coatings, and ending with strain gauge analysis. I hope these live sessions were helpful for the viewers. So those who are taking the exam, I encourage you to resolve your assignment questions, revisit the lecture problems also. And if you're interested, you can also watch the live sessions of other weeks to get yourself familiar with the concepts that are discussed. So I wish everyone who is taking the exam the best of luck. Thank you.